I will start then. So I am Paul Royal. I'm a research scientist in the College of Computing at the Georgia Institute of Technology and the Associate Director of the Georgia Tech Information Security Center. And today I will be talking about digital rights management for malicious software. There we go. All right, so here's the structure of my talk. And it begins with establishing just some common definitions for malware obfuscations that we will use as primitives when talking about malware DRM. So in the beginning, there was packing, so named because the original types of obfuscation tools would make the resulting executable smaller. Obviously, that's no longer necessarily the case, but in short, in the oversimplified diagram here, that I'm sure many of you already know, you take a program A, which contains some type of code. Program A could be malware, and you run it through an obfuscation tool to produce program A prime. And the whole point is that portions of program A's code have been made to appear as seemingly benign data, and that's it for that. A more recent type of obfuscation is ISA virtualization, as you'll find it in things like VM Protect or Archimedes Code Virtualizer. And in ISA virtualization, a program, for example, an x86 program, will have its machine code permanently transformed into bytecode for an arbitrary attacker-decided instruction set ISA, and the program semantics, the semantics of the original program, are fulfilled by the interpreter, which will be compatible with the interface, say x86, interpreting the bytecode. All right, so that's all the remedial material. So traditionally, malware has been analysis environment aware. It will use anti-debugging, anti-instrumentation, or virtual machine detection techniques to try and infer whether it's in an analysis environment. And if it detects, if one of those detections are successful, it won't run, or it'll emit deceptively benign behaviors, or a different set of deceptively malicious behaviors. But otherwise, it will run. However, there's no reason why you can't invert that model. And when you invert the model, you're basically exploiting or leveraging the fact that most malware is analyzed in an environment different than the originally infected host. So the idea with digital rights management for malware, given that when you take a copy of malware or share it, you're sort of infringing on the malware author's copyright. The idea is to employ traditional digital rights management techniques to prevent the corresponding program from running on a system different than the one that was originally infected. So one logical question is malware in some way or another already doing this? And the short answer is yes, for some small or more primitive representations of the idea. For example, Flashback was a large Mac OS X botnet. It grew to about 600,000 members in size. Towards the end, it was propagated by drive-by downloads. The drive-by download took the appearance of it was a malicious jar file, had two class files with an exploit for I think CV 2012-05-07, but it also had a small 40 kilobyte Mako binary, and that Mako binary was part of Flashback, but it was not a full version. That small binary acted as an intermediate download agent. It would use a standard Mac OS X API to obtain the hardware UUID. That's a numerical identifier that uniquely identifies a particular Apple device, and it would submit that to the command and control. The command and control would hash that with MD5, and then use that with RC4 to create a full version that was tailored to a system with that hardware UUID. The resulting full binary would repeat this process in order to decrypt the portions of itself required to execute, which means that if the hardware UUID of the system wasn't the same, the binary, the full version of Flashback, that particular instance of Flashback won't run. So Flashback is sort of doing something like DRM already. And then less than 6 months after Flashback, there were reports of Gauss, which, according to Kaspersky, is nation-state malware created to spy on on targets in the Middle East. Gauss has an encrypted payload. The decryption key is based on two pieces of system information, environment variable and file system information. A candidate key is combined with a salt and then once again fed to RC4. And Kaspersky really wanted to find out what was in this, and they were unable to. You can see the quote there. They tried a bunch of combinations, and they were not successful. And then they blogged about this and asked for help in determining what that key was. So now we have another instance of malware doing it. So the question is, how will malware that does it look in the future? And what impact will that have on what is now a multi-billion-dollar, effectively malware analysis appliance-based industry? So again, the goal of DRM for malware is to make automated analysis ineffective and unscalable. It's not necessarily to prevent one knowledgeable, well-trained human being from being able to break protections for one particular executable. And in order to achieve the goal, we're going to cryptographically bind a malware instance to the host that was infected, the original host. And specifically, I'm going to introduce two techniques for doing that, for implementing the approach. And those are host identity-based encryption, which I'll refer to as HIE, and instruction set localization, which I'll refer to as ISL. So with HIE, you have a diagrammatical representation of it that's similar to traditional packing, except instead of a randomly chosen encryption key, you're going to create an encryption key derived from host identity. And we'll talk more about host identity and how you bootstrap this process in the next few slides. But again, in short, you collect host information, and you derive from that information an encryption key, and that gets fed to the corresponding tool that will encrypt portions of the program. So one logical initial question to ask is, what do you encrypt with HIE in the actual malware instance? If you encrypt most of the binary, that might actually give an analyst an opportunity or a way to check when they're brute forcing a set of keys. So instead, it might be best to encrypt only certain critical mechanisms. For example, the domain names, the command and control domain names, are portions of the domain name generation algorithm. That way, the binary will still exhibit, for example, network behaviors, but they won't. The information that its output won't be actionable. In short. So, in terms of what information we want to comprise the host ID, there's a couple of properties ideally we'd like this information to have. We obviously want it to be unique. We want it to correctly or precisely identify a host. We want it to be relatively stable or invariant. But of course, the lifetime the lifetime of that information before it changes needs to be only as long as the malware campaign is. It can be as short as a few days or weeks. Unlike traditional DRM, we can't assume that we're going to have privilege on the host that we're gathering information from, and we also can't assume that we have special hardware, for example, that can perform attestation outside of the environment. So for Windows, the prototype host ID that we came up with uses a subset of the process environment block, specifically the username, the computer name, and the CPU identifier. It uses the MAC address as well. You can get GPU information using for example, the Windows API get adapter identifier. And we also use the user security identifier, SID, which is supposed to be randomly generated by the OS at installation time and unique across a Windows domain. Other potential candidates that you could use to create a host ID include USB device serial numbers. Multiple classes of USB devices are required to have a serial number and to be able to report that. And you can also consider the existence or registration information associated with proprietary software that is supposed to be on a target that is infected. For Android, it's actually much of the same. there's a subset of os.android.build fields, specifically the board, which is usually the code name. It's like Goldfish or Bravo, and the model, which would be like HTC1. We're also going to use a subset of proc CPU info, which specifically is the processor. Usually it's a label, and then proc CPU info in, or at least on the devices that I looked at, also has a serial number. So this is, again, I think, a good, unique piece of information. But perhaps the best is the Android ID field, which is in settings.secure. This is a randomly chosen 64-bit value created when the device first boots, and will actually change between, for example, if you were to reset the phone, the value would change, which can be an advantage. But in all cases, that's probably going to be part of any Android host ID. In terms of the key derivation function, the KDF itself we decided to use was bcrypt. The idea is simply the concatenation of all that information. And again, you need to choose your ID components thoughtfully to make sure that people cannot infer or brute force the information that comprises the ID and thus break host identity-based encryption. And then you want something like an iteration counter or work factor, and for bcrypt we decided that 10 was reasonable. Now, one shortcoming of Flashback, for example, how I ended up successfully analyzing Flashback by obtaining a copy of the intermediate download agent and then binding it to a virtual machine running Mac OS X. And that could also have been used that could also be used for HIE if you're not careful in your implementation. And in addition, you need to determine the host ID again before you actually install the full version, because the full version is based on the host ID. So you have to bootstrap it. So you'll use an intermediate download agent like Flashback, but unlike Flashback, the agent will have a URL into it that is basically a short-lived one-time use URL. That way, if a researcher obtains a copy of the agent, the URL will have been used, and they won't be able to use that agent to obtain a copy of their HIE protected binary bound to their environment. And obviously, this is similar to password reset procedures. So the advantages of HIE is that it's based on modern cryptography and that knowledge of how the key is derived. I mean, there could be presumably an API or a standard or specification for this. And that wouldn't affect the integrity of the protection, again, provided that the components comprise, the fields that make up the ID are well chosen. In addition, intelligence collected from one particular malware instance doesn't provide an advantage in analyzing another. That's another advantage. So HIE is, was enough to prevent, for example, Kaspersky from determining what the encrypted payload in Gauss was, but we don't, or at least I don't consider it sufficiently resistant to forgery. Thus, we're going to use another technique, instruction set localization, to effectively authenticate the malware client, the HIE protected agent, to the server using both host and network identity. And in doing so, we're also going to decouple the malicious functionality that's normally embedded in the executable in order to prevent offline analysis. And I'll describe what that means in the next few slides. So in short, the HIE protected binary doesn't have any embedded malicious functionality. It is just an interpreter for bytecode representing an attacker-decided instruction set architecture. And it will fulfill the instruction execution semantics, or the execution semantics of what the attacker wants to do by being fed tasks. Basically tasks that contain bytecode, and it will interpret that bytecode to execute. So you could, one implementation of ISL could basically involve creating a unique ISA for each host, or some derivation, some derived ISA. That can be difficult, so one alternative that I'll introduce in a few slides is using a task decryption key, using a common ISA, but a task decryption key that basically protects, that basically protects bytecode served to each host to make it specific to each host. So the diagram for instruction set localization looks similar to ISA virtualization or ISA virtualized malware. So again, you have the client, which is an HIE protected instance of malware. And obviously it also contains an emulator for tasks that will consist of bytecode served to it by the command and control. It will submit its host ID to the command and control. The command and control will gather its network ID. I'll talk about network ID shortly. And it will combine host and network ID into a central unique key. And that key will be used to encrypt tasks that will then be served back to the client. So in terms of what the network ID looks like, in our prototype, we have geolocation. So we'll take the IP address as is gathered again by the command and control, and we'll locate it to the state or province level, as we believe that this permits a certain necessary level of mobility. For example, if the target is a laptop. We'll also determine the corresponding autonomous system number. As sometimes geolocation information, geo-IP information may be outdated or non-existent. And as the network ID components are collected at the command and control, we believe that they cannot be forged, unless, of course, you can guess or effectively spoof sequence numbers in TCP. So again, instead of having an instruction set architecture that is unique to each target, you can have a common ISA and combine that with a task decryption key. So this key is basically assigned when the malware instance is delivered to the host. The network ID is determined when it goes to get when the intermediate agent goes to get the full version. And tasks to be served to the host at some later time will be encrypted with this ID. And in this case, the KDF is actually an HMAC, aka a keyed hash, with the corresponding key kept obviously on the command and control server. And that's to mitigate the unlikely occurrence where two different attackers have chosen the same host and network ID, and thus knowledge of what those are for one binary could be used to break the protections of another. So the HMAC basically makes that unique, even for the same target with different malware campaigns. So the advantages of ISL is that, again, the HIE protected binary is just an interpreter for bytecode, which means that if you don't interact with the command and control, you won't be able to know for example, offline means what it was intended to do. And similar to HIE, unless an analyst can correctly mimic both the host and network identity, tasks will not decrypt and thus will not execute. And then finally, almost from a software engineering perspective, similar to other interpreted languages like Java, task source code has hopefully enhanced portability, which means you could can modify write once, run anywhere to run anywhere to write once, infect anywhere. All right, so I'm going to talk a little bit about the properties of the operational security properties of HIE and ISL, and then propose some countermeasures and see what the effectiveness of those countermeasures might actually be. So both HIE and ISL again use the principles of modern cryptography, which means knowing how they work does not affect the integrity of their protections. Effectively, if you want to successfully analyze a binary that uses both HIE and ISL, you have to recreate the same environment. And again, without access to the original environment, if you want to try brute forcing, say the host identifier, you have to search the entire key space, which can be of arbitrary size. And some configurations, specifically in regards to the network identifier, may be impossible to duplicate. In addition, and it may be obvious, but I think it's worth mentioning, HIE and ISL are insensitive to analysis techniques, which means that, for example, the granularity of a certain type of analysis, like fine-grained versus coarse-grained analysis, doesn't affect their protections. You can only break them if you can correctly replicate the environment from a host and network identity perspective. Oh, sorry, from. So in terms of countermeasures, one straightforward countermeasure is to let the malware binary continue running on the originally infected host and analyze it there. And I don't think that most organizations would be happy with AV companies, for example, detecting something on a host and deciding that it's in their best interest from an intelligence gathering perspective to let it continue running on that host. And so this probably wouldn't work very well. You could also try using a high interaction honeypot. So you have a human being behind a honeypot attempting to replicate the circumstances of compromise. Obviously this doesn't really scale, and you may not be able to get coverage of all the malware that you're interested in. So that unfortunately doesn't seem like a great avenue either. You could attempt to collect and duplicate both host and network environment information. Again, it's going to be hard to duplicate information. It's going to be hard to duplicate the network as an antivirus company, because you'll need the same autonomous system number, and you'll need to be in the same state or province as all of your customers. And moreover, attackers, for example, may respond by deciding that one piece of host identity is now the target's Google authentication cookie, and that the target may have problems with submitting this piece of information to random organizations. So there is a possibility where a bunch of security companies could combine together and try and create basically shared or rented analysis system space. For example, like in every state, every autonomous system, or in as many as possible. But this would require a bunch of people working together who, frankly, I don't think have a very good track record of doing that. So that seems unlikely as well. So one other potential countermeasure is that you collect and duplicate only host identity, and then you record and replay network interactions you saw in another network to try and have the binary do meaningful things. And without an additional protection, this could perceivably bypass instruction set localization, but you can mitigate this by simply using SSL or TLS to encrypt the HIE protected binaries interactions with the command and control. Finally, you could virtualize everything in an organization and then make on-the-fly copies of virtual machines to perform analysis locally on some malware analysis appliance. Of course, not everything can be virtualized, and duplicating large numbers of virtual machines is going to create a real scalability challenge, especially presumably relative to the number of machines you would need to copy. Finally, you can employ an allergy attack. And that means you can basically make the information that would presumably be used by HIE and ISL protected binaries unstable. For example, you could change the MAC address for every program invocation, or the security identifier. And as a consequence, malware would not successfully run on the infected host. Right? However, this would also affect a variety of legitimate software. Including software that uses traditional DRM. And users would probably not be happy with, for example, them needing to get a DHCP lease every time a new program starts, et cetera, et cetera. And so this, I think, to some extent, the success of this potential countermeasure would depend on the willingness of users to accept security over usability. And I think we all know what they are going to choose. So, in conclusion, malware has traditionally been analysis environment aware. However, recent developments, such as those exhibited by Flashback and Gauss, show that malware can in fact be analysis environment oblivious, and that primitive DRM-like techniques as introduced by Flashback and Gauss can be matured into techniques like host identity encryption and instruction set localization. Thus, future work on the defensive malware analysis side must mitigate these protections if they can be mitigated, or instead examine alternatives to threat detection and analysis. Are there any questions?
All right, so there has to be at least one brave soul. Was it you back there? No?
I mean, I would love ideas, in particular because I've been creating large-scale malware analysis systems for about a decade now. So like that's actually my background. I'm more of a defensive tool-oriented kind of researcher, and I would like nothing more than to be able to continue doing what I've been doing. So if you have any ideas, please let me know.
Yeah, I have a question. For these technologies, have you ever looked into more hardcore like obfuscation or white box cryptography primitives to strengthen them?
I have not. But I would say that those can be supplementary to, well, I mean, even traditional obfuscation tools, I think HIE and ISL are not intended to be replacements, but rather supplements to the stuff we're already using. And I think the work can certainly be extended. For example, one thing I didn't mention about Gauss is that the way in which it creates a candidate host ID is actually somewhat non-deterministic until you actually have a working copy. Like it would look at environment variable information and file system information, then split over a semicolon separator and take all possible pairs, and it would just try each pair. So without actually knowing what the key is, you can't determine what information is used with the key. So that's potentially another extension as well. But I'm digressing.
Do you have problems with persisting after reboot and having malware that lasts longer than a session with these kind of techniques?
Well, it would depend on what information might change after a reboot, right? So I think for things like the security identifier, like that'll stay the same. The MAC address should stay the same. The Android ID should stay the same unless the device is reset. But that's probably also true, for example, for the SID in Windows. So, I mean, again, it's whatever the campaign is, finding the right combination of fields that will last as long as you need them to, I think is going to be key. It's the thought put into it and not necessarily a lock, stock, and barrel copy of what's in the slides.
Awesome. Well, I think, thank you very much. And that concludes Infiltrate.